So we have defined now these W's on the two parameters S and T, and also the W for L1 functions. And yeah, I'm going to use them later, and it's good to have maybe a few properties, in particular how they multiply. Of course, the fact that the U and the V have some multiplication rule, of course, also means if I'm multiplying different ones of the W's, I will get more or less a multiple of another W. So let me collect those properties in the following proposition. So first of all, the W's as a product of unitary operators, I mean the U, the V, and also this E factor is all unitary. So the product of them, of course, is also unitary. So all W of S comma T are unitary. And if I multiply two of them, then we have a very nice relation. So the Weyl relations can be rewritten in relations for multiplying two of the W's. So we have for all arguments which we need there, so for all, so I need 2S and I need 2T, T2 in R. Well, we have the following. If I'm multiplying W of S1 T1 with W of S2 D2, then the effect will be mainly that I'm adding the argument. So I will get W of S1 plus S2, comma T1 plus T2, and then of course I will get a phase factor, which one has to work out, and this will be e to the 1/2 I, and then I have S1 T2 minus S2 T1. Okay, so this is an easy exercise, and actually we also had this in one of the assignments. Those are things which, I mean, everybody should convince oneself that it's true. This is very easy and straightforward, but one really should check that it's okay. And so in particular, what we have here is of course, I mean, specific cases are, of course, if S and T both are equal to 0, then of course the W is just the identity operator. So maybe it's good to note also this. So the W of 0, 0 is the identity operator. And of course, if I take the adjoint of such a W, I will get another W where I'm just changing the sign of the arguments. So W S comma T star, this is W of minus S and minus T. And the unitarity, of course, means that this that W of S comma T times this W should be equal to 1, which of course is compatible with this multiplication rule and this relation here. Good, so that's for the WST. Then we have to understand also better what the WH for integrable functions is, and in particular it will be important that the mapping from H to WH is an injective mapping. Okay, so if H is different from 0, then this operator here will not be the 0 operator. So that's maybe the most important and maybe the most non-trivial statement I'm going to make here. So this map which sends H, L1 function, to WH, a bounded operator on our Hilbert space, this is injective. So which means that the WH is not the 0 operator if H is not a 0 function. That will be important later because we are going to build operators. In particular, we are looking for a projection operator, which we should try to get somehow in such a form. And of course, I mean, we want a projection onto the vacuum, and of course we should know that our projection is not a 0 object, otherwise there would not be a vacuum vector. Okay, so this is an important statement here. And then maybe for the calculations, it's also important to extend this product rule for if I'm multiplying two of the W's also to the functions. And this is again maybe a straightforward calculation which I'm going to write down and which everybody should check for him or herself. So if I have two functions, h1 and h2, integrable functions on R2, then we have that W h1 times wh2 is again of the form w of h for an h which will be calculated from h1 and h2 in a convolution-like form. So namely, I'm writing it down. So this, we have this, where first of all, of course, the h is again in L1, because otherwise this wouldn't make sense. So L1 in R2, and it is given by h of s comma t. So it is mainly convolution in the two dimensions of h1 and h2. So it's h1 of s minus, let's say, s twiddle, and t minus t twiddle. S twiddle and t twiddle are the new variables over which I'm going to integrate. Then I have h2 of s twiddle t twiddle, and then there will also be a phase factor corresponding to what I have here. So namely, I also have an e to the 1/2 I, and I'm getting here s t twiddle minus s twiddle t, and I'm integrating over s twiddle and t twiddle. Okay, so this is again something which everybody should try to check by himself. Okay, and so for the proof, maybe I'm saying a few words about part 2, this injectivity, because this is maybe not absolutely clear how this works. So the proof, so let's say 1 and 3 are just easy calculations, which I'm not going to do here. And for part 2, so let me assume that I have that w of h is equal to 0. And I have to see that then the h must also be equal to 0, or almost everywhere equal to 0 as an integrable function. So I assume wh is equal to 0. Yeah, okay, so this means I know, what is wh? Wh is this integral. So I know this integral is equal to 0, and I want to see that this function is equal to 0. Yeah, okay, so just having it for this integral maybe is not enough, but of course I can now multiply my wh with other w's. It still will be equal to 0, and then I can change this integral to other integrals, and then I have enough information to infer that h has to be equal to 0. Okay, so from this, I'm multiplying this equation with w minus x minus y on one side, and with w, x, and y on the other side, and of course it's still equal to 0. And this is true for all x and y in R. If this guy is equal to 0 and I'm multiplying it with some other bounded operators, then it's still equal to 0. Yeah, and so what have I now got here? So I have that 0 is now this guy here, but let us see what this is. So this is, let me write it down. So this is w minus x minus y, and then the wh, so this was the integral of hst wst ds dt, and I'm multiplying on the other side with the wxy. Okay, so this is equal to 0, but now this here, of course, I can calculate further, because I can bring this in the integral and multiply this with this, and then this is now a product of the w's for s and t, and for this, I mean, we have rules how to calculate, how to multiply this. So I can use those rules, and so what do I get? Okay, of course, you have to use that this integral is continuous in the right way, but all those things are quite easy to check, and in particular they are true. So I'm just going to use those. I can bring this under the integral, and then I have h of s comma t, and let me see. So what I'm doing, maybe let me first multiply this with this. So what is the effect of multiplying this? So I'm adding the argument, so I have here s minus x, and the second argument is t minus y, but I get a phase, and this phase is e to the 1/2 I, And what was the phase in this formula here? So it's first argument of the first guy times the second argument of the second guy, and the other way around. So in this case, the argument here is s. No, it's here x and s. So it's minus x times t. Yeah, so it's minus x times t, and then it is minus this times this, but with this minus sign, I will have a plus here, so it's plus y times s. Yeah, so this is the product of this w with this w, and then I'm still left with this w here, xy, and I have ds dt. Yeah, so I'm using now again this rule for multiplying this with this. Yeah, and let me continue here. Maybe I can now erase the definition of the w's. And so we are just adding the arguments again, and this means in the arguments the x and the y are just going away because this here cancels those, and but I will have an overall exponential phase factor. Yeah, so now the product of this and this, let me say it like this. So what is, so the w will just be this plus this, which is just w of x, and here I get just w of t, but I get a new phase factor, which is e to the 1/2 I, which of course does not cancel. So I mean, if I'm multiplying it from here with this and from here with this, of course in the arguments, the shifting cancels in the end, but the product of the two phase factors which I'm getting will not cancel away. So there will be something which is left over in the end. So namely in the second term I will get something which is e to the 1/2 I, and then I have the first argument, so it's s minus x times the second argument here minus the second argument here, t minus y times the first argument here. Is this okay? I hope so. Yeah, and you see now some parts cancel with the phase factor here. So namely the xy, no, the xy doesn't go away, but the sy, I have it here. Let me see. Does it cancel? No, actually it does not cancel. So what do I have here? I have the sy and I have, so okay, you see I have here xy and I have here yx, here with a plus sign, here with a minus sign, so this goes away, and the sy which I have here comes here with 1/2, and it comes here also with 1/2, so actually it will survive with a factor just with an I, and for the ys in the same way. So what I have here is I have this h s t, and then what remains of the phase is this factor here, but with a factor 2, because I have it again here. So it's e to the I sy minus tx, and then I'm just left with w st ds dt. And this guy is equal to 0. So that's what we have got now. That, I mean, we started from that this is 0 without this phase factor, but now we get it with this phase factor. But now you see what I'm doing here, this phase factor, I'm integrating over s and t. This is essentially taking the Fourier transform of the other function. So I'm integrating over st. So this is the Fourier transform at the point y and x of this function as a function in s and t. And this tells me that the Fourier transform of this function is equal to 0. Okay, and then because the Fourier transform is an injective thing, this tells me that the function itself is equal to 0. Yeah, okay, but maybe again this is operator valued. So in order to argue just with functions, again we should take inner products of this function. So maybe I So I have this as an operator equation, but now I take the inner product with vectors as before, f and g, and then what one has seen by this calculation is, so for all x and y, and for all f and g in the Hilbert space, and x and y of course are real numbers, we have that actually 0 is now the integral over hst e to the I s y minus tx, and now I'm taking the inner product applied to the operator here. So I'm taking here the inner product of f and w as t, and now ds dt. So this is equal to 0. Maybe that's now really something where I can really argue, because this is now the Fourier transform. Yeah, this is taking the Fourier transform at x and y, and I'm taking the Fourier transform of the product of those two functions in the variables x and t. So this tells me here that the Fourier transform of this times this is equal to 0. Yeah. Okay, so this means the Fourier transform of the function, so this is now a function in R2, I'm doing a Fourier transform in R2, so of the function which sends st to this times this, so h s comma t times the inner product between f w s t comma g, that this is equal to 0. So the Fourier transform of this is equal to 0. So this is the Fourier transform at the point yx, or maybe at the point minus yx. So this is 0 for all x and y. So this means the Fourier transform as a function is equal to 0, which means the original function itself must have been equal to 0. So this function here is equal to 0, and this is true for all f and g. And of course equal to 0 in the almost everywhere sense. Yeah, okay, so a bit more space to finish this argument. But that was now the main point. And now it just remains to see that not just this product of h and the w is equal to 0, but that this implies that the h itself is equal to 0. For which we should see that the w actually is not equal to 0, at least not for all choices of f and g. Okay, so this tells us by the injectivity of the Fourier transform that the function hst times f comma w st g is equal to 0 almost everywhere. So with respect to the two-dimensional Lebesgue measure. So this is a function of the variables s and t. Yeah. Okay, and now, of course, this guy here might, for some f and g's, might be 0. Okay, so we cannot say this is always for all s and t different from 0, which means this is equal to 0. But we have to say a little bit more precisely that if we know that this is equal to 0 for all f and g, then we know that without this guy here, this vector here has to be equal to 0. Okay, so this means that h s for each g, this guy here, w s comma t times g is equal to 0. And again, this is almost everywhere, and we have this for all g. So here we had this for all f and g in the Hilbert space. And now, if this here is equal to 0, then we can run over f, let's say, over an orthonormal basis. And this means the inner product of this vector with each element in orthonormal basis is equal to 0, which means the guy itself must be equal to 0. Yeah, one has to be a little bit careful because I have here almost everywhere. So this means for each f and g, I have a set of values s and t where the property doesn't have to be true. Okay, and so I mean, if I'm going to argue, so I have this for all f, which means that this guy is equal to 0, which means that this guy is equal to 0. I should not involve uncountably many f's for doing this argument. Okay, but I can run over a basis in my Hilbert space, which is countable, and then of course this guy has to be equal to 0. And this is true for all g, but now W is a unitary operator, so if g is different from 0, this guy here is a vector which is different from 0, and then if this multiple of this vector is equal to 0, then of course this vector here must be equal to 0, almost everywhere. Okay, so this means in the end we really have what we want, that h is equal to 0 almost everywhere. Good. Okay, so it's also quite straightforward calculation, but yeah, we have to see that the multiplication of w xy and w minus x minus y from both sides on our equation produces us essentially the Fourier transform of functions, and then we can argue with this and see that everything has to vanish. Good. Okay, so this is maybe the calculation, but the important point is just to remember, or to see that this mapping h to wh is really injective. So if this guy here is not 0, then this operator here is also not equal to 0.